All right, so we are beginning our final segment, well, our next to final segment on this course. And now we're going out to the farthest scales, the biggest scales. We're talking about cosmology and the origin and evolution of structure in our universe. The last segment of the course will be on the existence of life in the universe because it turns out it does have an intimate connection with the biggest scale context of our universe. We'll get to that on the last day of class, but we have probably both today, Monday, and then Wednesday will both be on just cosmology. So these are the things we're going to talk about. Let me get my little marker going here. We're going to talk about Olber's paradox, and then large-scale structure and its relation to dark matter, the discovery of the cosmic microwave background and what it means, and the evolution from there to dark energy, and yeah, an ET phone home. That's really, we're actually going to put that into a separate show. A separate show, by the way, which is already recorded because I did it as well for my Astro 25 class, which just concluded. All right, so the first point is, let's take ourselves back to Newton's time and imagine a universe that would make sense in a natural context. Again, obeying maybe to the letter of the law almost. Occam's razor. Simplicity is usually truer. So now we imagine a universe that does not have an edge. It doesn't have an edge because if it had an edge, then you'd have to ask, well, what's beyond the edge? And that's an embarrassing question. And so maybe we should just get rid of the question and say, well, there is no edge. It just goes on forever. A universe of, in Newton's time, we didn't think in terms of galaxies. We thought in terms of individual stars. But the argument holds well either way, whether you think in terms of stars or galaxies. So if the universe goes on forever, then you can ask also, well, has the universe always been here? And if you postulate a beginning to the universe, then you have to ask, well, what happened before the beginning? And that's embarrassing. So let's get rid of that question and say, well, gee, if you're going to postulate a God who's been here forever, then why can't you just postulate the universe itself, which we already know actually exists, as existing forever? So that's our base case that we're going to start with. A universe that has always existed. It's been infinite in space and time, no boundaries in either one. It turns out there's an extremely easy way to rule that out. And that is that if you look out in space, sooner or later, every line of sight is going to run into a star. And the reason for that is because the stars go on forever. That's our postulate. And just like these trees here, no matter where you look, sooner or later you're going to run into a tree. So we got a forest and trees problem. Similarly for the stars, and since there's been infinite time for the light to get to you from the stars, then it has indeed gotten to you. And that means that the entire night sky should look as bright as the surface of a typical star. And we know how bright that is because our sun is a typical star and is blindingly bright, and it's 6,000 degrees. And that means you are inside of a 6,000 degree oven. And of course, that means you are going to be 6,000 degrees and you'll be dead. So clearly, that is not the situation. Newton himself realized this, but he couldn't seem to get the rest of the world to appreciate the real paradox there. And it waited for another couple of hundred years until Olbers, a famous observer in the 1800s, astronomer, pointed it out again, and this time the paradox of it all stuck. And so it came to be known as Olber's paradox. Why is the night sky black if the universe goes on forever? So what we've done basically is a little proof by contradiction. So either one or both of our starting assumptions must be wrong. Either the universe is not infinite in space, or it had a beginning. It's not infinite in time. One of those two must be the new case. All right, now it actually gets a little more complex because of the issue of redshift, but the basic idea actually remains. So could the universe be finite in time? Could the universe have had a beginning? Well, the Hubble Deep Field, this was a 3-day long exposure taken by the Hubble Space Telescope fairly early in its life. Took an incredibly long, I don't know, 40 hours, 50 hours, I forget. This is back in the mid-1990s, 25 years ago or so. It took the ultra deep field, and what we have circled here in green are galaxies that are incredibly far away. And you'll notice that each of these is a little teeny tiny red dot. I don't know if you can see that there's a redness there. These are distant galaxies. Even the more nearby galaxies, though, you can see, are not dominated by the usual spirals that we see in our local neighborhood. Spirals and barred spirals make up most of the bright galaxies in today's universe. Now remember, as you're looking out in space, you're looking back in time because the speed of light is finite. So if this galaxy here is 1 billion light years away, then you're seeing it not as it is today, but as it was 1 billion years ago. And I want you to realize that as you look out, you're seeing galaxies that are more and more typically irregular and colliding and elliptical, the products, as we saw, of galaxy collisions, or irregulars like this one here. And so basically galaxies look different as you go out. They don't look as relaxed. They look more early in their evolution, a more collisional and violent and unsteady state situation. So distant galaxies really do look different. We also know, as we already saw in the last chapter, that active galaxies are more common. Active galaxies being galaxies that put out most of their light in something other than starlight. They're dominated by X-rays and radio waves and ultraviolet and infrared and a little of everything. And a lot of that is from the black hole at the cores of the galaxies, and the black holes are active because there's still a lot of new infalling stuff that has low enough angular momentum to fall straight to the middle and power the accretion disks around those black holes. And quasars are more common distant in the distance. And in fact, not only they're more common, there are no quasars in today's universe. There are no quasars that are nearby. The nearest quasar is 3 billion light years away. That means 3 billion years ago. That's a quarter of the way back to the beginning of time. So clearly the universe is evolving. So that's our conclusion from these observations I'm summarizing now. We do not live in a static, steady state universe. Now I remember back when I was a kid, and I was first getting interested in astronomy in the early 1960s, and I was actually kind of a fan of the steady state universe. The idea that somehow, some way, the universe has always existed in pretty much the same way it looks now. Individual characters come and go, just like individual people come and go. But the humanity on Earth has been around for a very long time. Maybe the universe has been around infinitely. It was sort of philosophically satisfying, and also because I was pretty down on the idea of a godlike creation to the universe, religion in general. As you all know, I still am. However, the steady state universe turns out to be wrong. So, oh well. And we'll see how we disprove that. So the first notion to realize is something we already talked about before at the end of talking about the distance ladder, and that is the Hubble law, the Hubble expansion. So Hubble discovered in the 1920s, and of course the observations have been extended to much farther distances now, that the galaxies are moving away from us. All galaxies, virtually all galaxies, are moving away. Only a few nearby galaxies are moving towards us. And they're moving in such a way that if you look at galaxies twice as far away, they're moving away from us, as it turns out, twice as fast. And if they're 3 times farther away, they're moving 3 times as fast. And it's exactly the kind of expansion that you would get if you're thinking about raisins in a raisin cake. So there's a famous analogy that still holds as a great analogy today, good enough to actually show a picture. I'll do that in a moment. But think about the implications of that. So if the galaxies are moving away, then if we run the movie backwards, we're going to end up having a universe that is more crowded. And if you go back far enough, the galaxies are even on top of each other. Clearly that's got to be a time before the galaxies had even formed. And if you go back further still, the galaxies and even the stars would be on top of each other. And clearly that's got to be a time before the galaxies and the stars had even formed. And all you must have at that point is just the raw material out of which stars are formed, which is almost all hydrogen gas, a little bit of helium. So it suggests the idea that maybe the universe began in a hot, dense early phase, and perhaps even in a singularity, a Big Bang. Now the word Big Bang was coined by Fred Hoyle, and he actually wasn't a fan of the Big Bang idea at all. And he coined it as a term of derision, a term, a put down of the whole idea. But the name stuck, probably because it just rolls off the tongue so nicely. Big Bang, two B's, two syllables. I mean, what could be simpler? What could be easier to say? So it stuck, and we use it now. We do not use it as a term of derision because the observational evidence to support it is now overwhelmingly large. But yeah, so there you go, raisin cake. So imagine the raisins, and the nearby raisins are going to recede from you. Okay, so that's us. Now in this particular cake, there is one problem. There's a boundary to the cake. So what you really have to imagine to get this analogy right is forget the boundary. This is a cake. It is a big cake. I mean, it's a really big cake. It's a cake so big that there is no boundary on here. The boundary is so far away, it's meaningless to even talk about it, at least at this point. So it doesn't really matter what raisin you sit yourself on. Every raisin is going to see the other raisins moving away. So this raisin here is moving away, but slowly, because there isn't much yeast between us. But this one's moving away faster because there's more yeast. And if you go to raisins really far away, then they're moving away really fast. In fact, at a certain point, if you continue that, you might think, well, gee, Rick, that seems to imply that if you go far enough away, the galaxies are moving away from us faster than the speed of light. That makes no sense. The whole idea must be bogus. No, it's not. And we'll come back to that. But first of all, we want to look for observational consequences that go beyond just the Hubble flow expansion. So as you go back in time, the density goes up, and you go back far enough again. You have raw material, just gas, hydrogen gas. If you go back far enough, then that gas is dense enough that it is at 3,000 degrees. So just imagine gas in the piston of a car. So as you press that gas, and that gas mixture, gasoline in this case, mixture, then it'll get hot enough to eventually ignite with help from your spark plugs. And actually, you don't even need spark plugs if it's a diesel engine. And that tells you that temperature and density go together. If you press them in such a way that the heat cannot flow outwards, and the heat can't flow outwards here because there is no outwards, and we're talking about the whole universe. So the temperature just goes up, and there's a very simple relationship between the density and the temperature. We'll show you that in a second. But anyway, the temperature goes up as you go back, and you'll find that if you get to a time only 300,000 years after the supposed Big Bang, the moment when everything would be at the same place at the same time, the temperature of this gas is 3,000 degrees, and that's a very magic temperature. That's the temperature at which hydrogen goes from being an ionized gas to being a neutral gas. So as a neutral gas, we have a proton and an electron going around it. And we already know from chapter 5 that the only way that a neutral atom can interact with light is to have the electron move between bound, discrete, quantized orbitals. And the large majority of the photons of light that are moving around out there are not going to have the right wavelengths to do that. So a neutral gas is pretty much transparent. You can look right through it. Yeah, there's a few wavelengths where the light is blocked, absorbed, scattered, but the vast majority of the wavelengths you can see right through. But if you go back before that time, then the temperature of the universe is so hot that the hydrogen is an ionized gas, and you can't see through that. Okay, an ionized gas is opaque. So, drawing a picture of that, you would see a universe getting denser and denser, and the galaxies until eventually be on top of each other, and then the stars would be on top of each other, and then you'd see a gas, but you wouldn't really see the gas because it's still transparent. And you go back and you go back and you're back before the time of stars and galaxies, and so there's nothing really to see, except it finally gets to a point where now it's 3,000 degrees, and as you run the movie backwards further, suddenly you can see. You can see the opaque surface of that hot gas. And so the prediction is that if there really was a Big Bang, you ought to be able to see 3,000 degree gas radiating at us from all directions. Now you might say, well, Rick, you just told us that, wait a minute, if we're surrounded by stars infinitely, they'd all be filling up every last square arcsecond of sky, and they would make us 6,000 degrees, like the surface of a star. So, okay, this is a little cooler, 3,000 degrees, but still, we'd be baked, we'd be cooked, we'd be dissolved, we'd be burnt to a crisp, we'd be ionized. We don't see that. Yeah, okay, good thinking. But there's one more ingredient you have to add in, and that is, remember, the Hubble expansion. So the farther away this stuff is, the faster it's moving away from us. And it turns out when you get to this point, only a third of 1 million years after the Big Bang, that stuff is moving away from you at 99.9% of the speed of light. And that means, as it turns out, that light will be redshifted then. And it turns out if you take a thermal spectrum of, just like starlight, take a thermal spectrum and then you redshift every single photon by the same amount, by the same fraction, same factor, if you will. It's going to be larger than 1, not really a fraction. It turns out if you redshift all of those photons, you will still have a thermal spectrum. And so you can still meaningfully apply a temperature to the radiation that you see. It doesn't literally mean that the gas is at that temperature exactly. It's really a spectrum of light from a distant time when it was actually much hotter. But we can apply a temperature to this. That's the interesting thing. It's just part of the way the laws of light work. Okay, so we should say a 3,000 degree sky, but redshifted by a factor of a little more than 1,000. And so it turns out to be a very simple thing to apply that same factor to this temperature of 3,000 and get what you should actually expect. And that is a temperature of about 2.7. Sorry, this looks like children's drawings, but it's our wonderful software here. 2.7 degrees Kelvin. That is very cold, okay? 2 degrees above absolute zero. And that kind of thermal spectrum does not radiate in the visible light like 3,000 degree red giants do. And it doesn't even radiate in the infrared. It radiates all the way out into the microwave. Uh-oh, I misspelled microwave. I'll fix it at some point. Microwaves, yeah. Maybe more memorable because it's misspelled. Anyway, microwaves. So that's what we should actually see. That's the real observational test. So photons were first able to travel freely with little chance of further absorptions beginning 300,000 years after the Big Bang. The universe was opaque until then, so you cannot see through that and see what the universe looked like earlier than this, not directly. But this cosmic microwave background in all directions should be observable. In fact, 99% of all the photons in the universe should be cosmic microwave background photons. So this graph just shows temperature as a function of time. This is a very compressed log scale. 10 to the 15th seconds, that's about where we are today. That's how old the universe is, measured in seconds. You could go back all the way to 10 to the minus 33 seconds before you get to the quantum time, and then you could go back further than that if you want. And, well, maybe that's not right. Maybe 10 to the minus 45 is the time. 10 to the minus 33 seconds is different. Anyway, the temperature goes up. It goes up in a log-log scale linearly. And that's because it's an adiabatic expansion.